Good morning, class. We are looking at chapter 2 review, limits and derivatives. And that is the synopsis of what will be covered in the exam. Again, I want to emphasize that when you get comfortable with this practice test exam review, I call that, you will have an easy time with the exam. So let's quickly recap what we've done already. So these are the sections covered in, just grab the annotation for now. These are the sections we're going to cover: the tangent and velocity problems, limits of a function, calculating limits using the limit laws, the precise definition, continuity, limits at infinity, horizontal asymptotes, derivatives and rates of change, the derivative as a function. And in this page, we discussed the concept of a limit. It is important to know when we are interested in finding the limit of f of x as x approaches a, and that's equal L, that means we are not interested in what happens at a, but near a, in which case the left-sided limits must be identical. And in all these three cases, the limits as x approaches a is the same thing, which is L. Part A is also continuous at a because f of a is f of L, and that's the definition of a continuity. In this case, f of a is defined, but it's not equal to L, it's equal to some other value, in this case b. And in the third case, f of a is simply missing, it's undefined. All of them tell us we have the same limit, but it's discontinuous at a. We looked at this case from a different point of view, numerical point of view, by coming close to one from both sides, graphical point of view, and more importantly, algebraic point of view. All of them result in the same answer, namely 1/2. We continue with limit laws, the concept of a direct substitution, and the squeeze theorem. The squeeze theorem says if a function g of x is in between f and h, when x is near a, except possibly at a, and the limit of f of x and h of x, both of them as x approaches a exist and is equal to any value, for example, L, then the middle function, the limit of g of x as x approaches a, gives us the same result. Looking at the limits, one-sided limits, whether the function has a limit or not at a specific point. Limits at infinity results in VA, vertical asymptotes. And the best course of action is to plug in and observe when you want to evaluate a limit. If it gives you a number, you're done. If it's 0 over a number, it's 0, it's done. If it's a number over 0, just make sure you understand the difference between infinity and negative infinity. Mostly we end up with indeterminate form. Some forms of indeterminate forms are as follows: 0 over 0, infinity over infinity, infinity minus infinity. In these cases, the first one, we end up with 0 over 0. Conjugate is the answer. For parts B and C, we have to figure out the denominator. 0 approaches from the left or right. And in these two cases, we end up 0 over 0. The first one requires factoring, the next one conjugate. In this one, the first one gives us the answer. The second one, LCD, does the job. In this case, we use the limit laws to get to the answer. In this case, we use the squeeze theorem. And the squeeze theorem is extremely important, and the way we approach it. One-sided limit will help us get to the answer, which is there is no limit. The precise definition, we basically are going with this definition, whatever the value of epsilon larger than 0, there is a delta larger than 0, such that this line segment is read such that if the absolute value of x minus a is less than delta, that results in absolute value of f of x minus l is less than epsilon. Meaning, if we wanted small distance between the functional value and L, in this case, then what happens between the A, whatever A might be, and in the vicinity of that, what distance will guarantee this? What distance? And if any distance will do the job, as it is the case here, for example, if any distance can do the job, then anything less than that will also do the job. In this case, when we went over that, a smaller number than 0.4 will always do the job. In order to prove the limit in this case is equal to the given value, you start again with this definition that I mentioned, and you replace the A, you replace the f of x, you replace the L, and that gives you the definition for this specific case. And then you start with the absolute value of f of x minus L less than epsilon. You work your way in order to find a relationship between delta and epsilon. And then the reverse process, the reverse steps proves that it works. Continuity, when the limit and the functional value are identical, the function is continuous at that given point. In this example, when we take a limit, if we set it to the functional value at x equals 5, which is c, we come up with a continuous function at x equals 5. The same thing happens for this case. This function, this piecewise defined function, is continuous everywhere. So you check the endpoint. The intermediate value theorem says that if a function is continuous on the closed interval of a to b, and n is any number between f of a and f of b, where the two values are not equal, there must exist a number seen a and b such that f of c equals n. And normally we use that to find roots. By roots, we mean x-intercepts or zeros of a function. Limits of function at infinity and the concept of a horizontal asymptote, which is the following definition: the limit of f of x as x approaches minus infinity is L, or as x approaches positive infinity is L, then y equals L is the equation of a HH for short of horizontal asymptotes. Vertical asymptotes were already discussed. And in this case, all of them end up being 0 over 0 because the variable txn, whatever it might be, it's approaching infinity, you divide by, and this is a rational expression, you divide by highest degree term in the denominator, you work it out. The same thing here, and this one you multiply by the conjugate. You plug in for part A, you get to the answer. For part B, you treat it as a rational expression, although it's not. Because the numerator and the denominator are not polynomials to be rational. So it's not. So you divide by highest value in the denominator, which is e to the power of t. In this case, last one, you do the factoring and it will do the job. This one, when you use the limit laws, the second one fails because sine and cosine, when you're taking a limit as x goes to infinity, it oscillates between -1 and 1. In part B, it's not a rational expression, it's a fractional expression. You divide by e to the power of 3x. Part A, very straightforward. Remembering the graph of ln x will do the job, and part B uses the squeeze theorem. And finally, here we were trying to find asymptotes. And horizontal asymptotes, you take a limit of the function as x approaches plus minus infinity, vertical asymptotes. Basically, you set the denominator equal to 0. And for part B, we're interested in finding a function, and we got one possible answer using the VAs. There are two of them, and HA, and of course, this is one possibility, and there are more possible answers, but this is one possible answer. So we are going to move on now to new stuff. All right. Derivatives and rates of change, tangent lines, and the derivative as a function. First and foremost, I want to remind you of this formula that everybody is familiar with, known as a slope of a line. So if two pairs are given, we know how to find the slope. Rise over run. In calculus, we call them delta y over delta x, which means y sub 2 minus y sub 1 over x sub 2 minus x sub 1. This is also known as the average rate of change of y with respect to x. And so this is, if you are dealing with a function and pick two pairs, connect them, and draw a line, that line is called a secant line, and this is the slope of that secant line. Now, this is one way to discuss that, as we have seen it in elementary algebra. Now, as we look at this graph, if we call this A and we call this X, I hope you realize this is identical to this, and it's rise over run. So the same as the slope as before. If we call this A and this distance H, so this is A plus H, and we go through the same process, rise over run, it gives us f of A plus H minus f of A over H. F of A plus H minus f of A, and then A plus H minus A gives us H. If we call this point B, which means now instead of f of x, we have f of B, then it gives rise to f of B minus f of A over B minus A, meaning all of them are the same thing, the good old slope. Now, we also call him the difference quotient. And for a difference quotient, most of the time we use this one to represent the difference quotient, but they all mean absolutely the same thing. Now, the tangent line is the limiting position of the secant line PQ as Q approaches P. So if this Q moves and gets closer and closer to P, what happens? Look at this one. We have the secant line and the next one and the next one, and ultimately you get to this line, which has only one point of connection, and it's called the tangent line at point P, which is therefore following this. M of the secant line versus the M of the tangent line would be the limit of M of this PQ as a Q approaches P. Or if you look at this one, as X approaches A, this one as X approaches A. For this one, as H approaches 0. I hope you understand the concept. So M or F prime of A uses these two definitions. The limit of f of x minus f of A over x minus A as x approaches A, or the limit of f of A plus H minus f of A over H as H approaches 0. Now, we know standard form of an equation of a line: point slope ax plus by equals c, point slope y minus y1 equals m times x minus x of 1, and slope intercept form is y equals mx plus b. And we use the point slope, and I hope you realize this formula is really the point slope. You don't have to memorize it. Y minus f of a is y sub 1. F prime of a is m, x minus a is x sub 1. And of course, we should solve it for y, put it in slope-intercept form as always. And another way of approaching this is if this is x and this distance is h or delta x, and now when we look at this one, it's specifically at a, but instead of this a, if we use x, it gives us the definition for f prime of x, which is the limit of f of x plus h minus f of x over h as h approaches 0. And if you decide to use that, you have to keep the a at a and do not change it. And when you're done, it becomes f prime of a, and you change the a to x. But we will look at both definitions. But for now, let's start by finding the derivative of the function using this definition that is given. I will look at the slope of a tangent line in a moment, but I figured I want to do this. By the way, many may know already that this takes a split second using formulas, but you have to use the definition for this specific section. So we're going to plug in. So according to this formula for this one, f prime of x is the limit of 5x plus 1, we want to use x plus h, becomes 5 times x plus h plus 1 minus f of x minus the parentheses 5x plus 1 over h as h approaches 0. So I hope we can see this, which is elementary algebra. Now, you have to work on this algebraically, finish the job, get to the answer. So all we have to do, distribute, and we get 5x plus 5h plus 1 minus 5x minus 1. And we notice that 5x and minus 5x cancel each other. 1 and negative 1 cancel each other. And we are left with 5h in the numerator. And h cancels out the h, and the answer is 5. Again, we could use the formula and get to 5 in a split second. However, we are using definitions for this section. We're going to do the same thing for part B. We're going to write this for f of x equals 2 over x. So f prime is the limit as h approaches 0 of what is f of x plus h, 2 over x plus h, minus f of x, just write this, over h as h approaches 0. So again, this is f of x plus h. By the way, if you plug in, obviously you get 0 over 0. And therefore, it requires the techniques that we've discussed regarding limits, and that would be using LCD. The least common denominator. And remember what you have here. You have a complex fraction. You happen to have 1 and 2 fractions, but you may have even more. Maybe you have a bunch in the denominator. So you find the LCD for all of those fractions. For these two, it's just x times x plus h. So you multiply and divide by it. The reason you do that, because this expression is equal to 1, and that's okay. So if I multiply this by the top, the first one, x plus h, goes away, I get 2 times x. The second one, minus x, goes away, 2 times x plus h. What about the denominator? You never, ever touch the denominator. You keep it as a product, because remember, it is the 0 in the denominator that is creating the problem. So you don't distribute it, you keep it as a product. And so what happens? All we have to do, distribute and simplify the numerator. So 2x minus 2x minus 2h And the numerator is simply negative 2h. As you can see, the h cancels out the h in the denominator. This is what you end up with. And if you replace the h with 0, the denominator is x times x, or x squared. The final answer is negative 2x squared. We want to find an equation of a tangent line to the graph of this function. F of x is square root of 3x plus 1 at x equals 8. We can find f prime of a two different ways, using just f prime of a, or just start with f prime of x in general and at the end change it. So we're going to stick with f prime of x. Let's generalize it. F prime of x is the limit of f of x plus h minus f of x over h. Now, I want to make sure everybody understands, if I'm interested in finding the equation of a line, any line, you need two things. You need a pair, which means eight comma what? If you plug in 3 times 8, 24 plus 1 is 25, and its square root is 5. So you have 8 comma 5. And you need the slope. So the slope, we're going to go through the process of finding it by definition. All right, so we got the pair. And by the way, sometimes they give you a pair, 8 comma 5. Sometimes they just give you the x coordinate. You can figure out the y by plugging it into the original function. So with that being the case, f prime is the limit of f of x plus h. So what is the f of x plus h? Square root of 3 times x plus h plus 1. And then minus f of x, just write this over h. So this is f of x plus h. Needless to say, if you plug in, you end up with 0 over 0, and that's an indeterminate form. We need to find a technique to fix the problem. The technique is called conjugate. So we're going to multiply by the conjugate of the numerator, and we're going to divide by it. This one, simply you change it to a plus sign. You put it here and here. So this is the conjugate, meaning if you have a minus b, the conjugate is a plus b, and the answer is a squared minus b squared. So again, what happens to the denominator? Nothing. You keep it as a product. What happens to the numerator? According to this comes out minus this comes out. So a squared minus b squared, the first one gets squared up and it comes out. And so does the last one. So we're going to write 3x plus 3h plus 1 minus 3x minus 1. As far as the denominator, we don't touch it. So clearly, (3x) and minus 3x cancel each other. Positive 1, negative 1 cancel each other. The numerator is 3h, and we can cancel out the h from the top and the bottom. And now that h is gone from the bottom, you can replace the h with 0. When you do that, this becomes 3x plus 1, and I hope you realize that the two are identical. That was the same thing. Remember, we are dropping the h when you plug in, and so we have 2 of that. So f prime is 3 over 2 square root of 3x plus b. Is this the slope? Absolutely not. This is f prime of x. So what is the slope? When you fix the x value at whatever point that is given, in this case 8, then it becomes the slope. Clearly, when you put 8, you get 5 here. Remember that? 5, right? 2 times 5 is 10, so 3 over 10 is the slope, and the pair, and we use the point slope. Y minus y1 equals m times x minus x of 1. Y minus 5 equals 3 over 10 times x minus 8, elementary algebra. And let's quickly just show everybody that this means 3 over 10 x minus 24 over 10 or 12 over 5. We are going to add the 5 to both sides, and you know that's 25 over 5. With that one, gives us 13 over 5. Now, of course, so this is your final answer. This is the equation of a tangent line. Remember, the pair belongs to the original function, also belongs to the tangent line. If you plug in 8 into the tangent line, must give you 5. So that's one way to check, assuming this one is correct, because that we have been through the process. Then how do you make sure that this slope intercept form is correct? If you plug in the x, you must get the y, whatever the value may be. The graph of a function is given. We want to use that to sketch the graph of the derivative f prime. It's a sketching, it's a rough sketch. And so there are a few things I want you to notice. Relative extrema, peaks and valleys. So relative mean, relative max, relative mean, at which point if you were to draw a tangent line, f prime is 0. Where f prime is positive, f is increasing. So it's increasing here. Looks like almost a line with a positive slope, increasing here, decreasing here, decreasing here. When f prime is negative, another simple definition of increasing is when x gets larger, so does y. And for the decreasing, when x gets larger, y gets smaller. And I want you to notice this case, and a rough sketch for that, I'll quickly show you. For this one, corresponds to 0. For this one corresponds to 0. Corresponds to 0. I'm going to sort of graph the sketch, if you will, of f prime in the same set of axes, and then I'll show you a better graph. Notice that f prime is decreasing here. So that means it's below the x-axis. It's also decreasing here, which means below the x-axis. But it has to come back to the 0 again, remember, because at c it becomes 0. And it is increasing in those areas. So if it's increasing here, it has to go up. But again, it has to come back to 0. If it's increasing here, it has to go up. Now, of course, I'll show you a better graph in a moment. Before I do that, I want to discuss this point that is given. They have done their best to draw a tangent line. They have picked up 2 pairs and they have calculated the slope. And what this means, the slope is 3/2. It means that on the graph of f prime, we have a pair with 5, 3/2 or 1.5. So let me clean up the mess and show you the graph. So 5, 3/2 here is shown here. It's a rough sketch. Now I'm going to start with the simplest example. If I want to come up with the slope graph of f prime for a line, all I have to do calculate its slope. And to calculate the slope, I need a couple of pairs. Obviously, this is 0, 0, and this is 1, 3. I want to make sure everybody can see what's happening. This one is number 6. So the scale along the y-axis doesn't have to be the same along the x-axis. That's why this point is 1, 3. And clearly the slope becomes m equals 3. And for any line, if they want you to graph its derivative, y equals that value of m, which is a horizontal line. So the answer is y equals 3. Because m is 3, y equals 3. And so that's the answer. So any line, the only line that doesn't have it, if you happen to have a vertical line, because the slope is undefined, has no solution. Otherwise, everything has solution. And any horizontal line, the slope is 0, then y equals 0, which is the x-axis, would be the answer. For this case, first notice the two easy points. You notice we have these two. They correspond to 0 and 0 here. And this is increasing, so above the x-axis. This is increasing above the x-axis. Decreasing below the x-axis. And the graph looks like that. Rough sketch. For this one, again, this corresponds to 0, 0, if you will. Decreasing. So below the x-axis. Increasing. That means if, when I say increasing, obviously f prime is positive. So above the x-axis. And it, this is obviously a better graph. But my point being, you can easily figure out what's going on. The next thing I want to discuss, how can a function fail to be differentiable? Normally, there are three ways. We have a sharp corner, we have a discontinuity, and we have a vertical tangent line, in short. So a quick discussion for each case. A corner or kink, the graph of f has no tangent line at this point. The left and right limits are different. So the point is, where do you draw and how do you draw the tangent line? If f is not continuous at a, then f is not differentiable at a. So at any discontinuity, for instance, a jump, f fails to be differentiable. So again, for this point, where do you draw the tangent line? Discontinuity can't do the job. A vertical tangent line, it's when the limit of the absolute value of f prime as x approaches a is infinity, meaning either infinity or negative infinity from both sides. So the graph of a function f of x has a vertical tangent line at the point a comma f of a if the limit of f prime of x as x approaches is minus infinity or infinity and not both, meaning the derivative of the derivative is infinity or negative infinity. We also have something called cusp, in which case the derivative from one side is infinity, the other side is negative infinity. As you can see it, for example, here for 0, the limit of f prime as x approaches 0 from the right is infinity, from the left is negative infinity, which means when the graph of the function becomes vertical and then virtually doubles back on itself, such pattern signals the presence of what is known as a vertical cusp. In general, we say the graph of f of x has a vertical cusp at the pair if this happens, as I mentioned. And it's sometimes not easy to distinguish between these two. But I'm going to go over a simple example, and hopefully with that example, we can sort of see the graph clearly tells us which one is which. So for example, here, the question is, given the function, where the function fails to be differentiable, clearly, for this case, it fails at x equals 0 because it's discontinuous, at x equals 3 because we have a vertical tangent line. I'm going to go over this concept in a moment with more details. This one, clearly at x equals -1, there's a discontinuity. And at x equals 2, we have a sharp corner. And what I want to mention is that one may not distinguish between these two. And I want to tell you that actually it's pretty easy. If you look at the graph, this one looks like a V shape. V shape. Now, either V shape or upside down V shape. But this one seems to go up vertically. It's really, I mean, it doesn't look like a V shape. So I think we can distinguish between a vertical tangent line and a V shape, I hope. All right. The graph of a function f is given. Use it to sketch the graph of the derivative f prime. Well, either we can read the following numbers or they are given to us. So they will help us calculate the slope for each line segment. In other words, we have 1, 2, 3, 4 line segments. First, I want to calculate the slope for each case. If I want to calculate the slope for this case, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So the top is -1. The bottom is +2. And the slope is -1/2 for this case. We can work out the rest of them. If this is -1/2, this is +1/2. I hope you can see that. This is clearly slope equals +1, and therefore this is clearly -1. You can calculate them. You have those pairs. Now, how do we graph this? I want to make sure we understand. If we had, let's assume we had this line segment and nothing else. If I had this line segment, I would just graph y equals -1/2. In other words, let's say this is -1, this is +1. Then I would graph this line, assuming this was a line, not a line segment, okay? But as you know, this is not a line, it's a line segment. So let me clean this up. So this point has a sharp corner. So this point has a hole, and we don't have the right side of it. So corresponding to this, we have this. And if that works, the same thing happens for the rest of them. For example, this one, m equals 1. So you draw m equals 1. There is a hole here. There is a hole here. So for this one, There's a hole here. There's a hole here. And you continue with the rest of it. So let's clean up the mess and show the graph for all of this. All right. Let's continue on. We are interested in finding the limit of the square root of 1 plus 4x to the power of 6 over 2 minus x cubed as x approaches minus infinity. Now, remember what happens when we are dealing with a rational expression. Assuming it was a rational expression, and it's not. The reason it's not a rational expression because of the expression in the numerator. It is not a polynomial, remember. Polynomial over polynomial means a rational expression. And if it were a rational expression, whether x approaches infinity or negative infinity, the technique is to divide by highest degree term in the denominator. So we can use the same technique in the following manner. We notice that the highest degree, this is, by the way, 4x to the power of 6 plus 1, or 1 plus 4x to the power of 6 makes no difference, or any format that involves that. We can factor out x to the power of 6 in this method. If I take x to the power of 6, obviously this gives me 4, but what does this one give me? 1 over x to the power of 6. And it's important to learn this method also as a calculus student. So why are we doing that? So I'm taking the highest degree term inside the radical sign, and I factor this out. So I factor x to the power of 6. Now, the first piece, 1 over x to the power of 6, and the last one is 4. Again, if you have any doubts, multiply this to this. Is the way you deal with a case like this. Now, if x is approaching infinity versus negative infinity, there are differences. And I'm going to remind you about the absolute value of x and its definition. As you recall, absolute value of x, let me just write it here, is defined as x if x is larger than or equal to 0, minus x if it's less than 0. Why is it writing like this? Let's see if I need it. So absolute value of x is x if x is larger than or equal to 0, minus x otherwise. Therefore, it gives rise to the following. In case of a limit as x approaches infinity for x larger than 0, if you recall, the square root of x squared is absolute value of x. And then you decide what it becomes. In this case, when x is approaching positive infinity, becomes x. But if it's approaching negative infinity and based on this becomes minus x doesn't mean a negative value. It means the opposite of x. And that's important to understand. The opposite of x happens when x is negative. In essence, this tells you that this expression is positive. So that's how you make this positive. So with that being the case, x cubed is square root of x to the power of 6 if x is positive, but it's negative of that if x is negative. And with that being the case, this can come out as x cubed if x is approaching positive infinity. Positive infinity. But now it can only come out as negative x cubed because of this negative infinity. So I want to make sure everybody understand that here's the situation. Because this is approaching negative infinity, we have this negative sign. And that is extremely important for everybody to follow. So now we can divide the top and the bottom by highest degree term in the denominator, namely x cubed. So if we divide the top by x cubed, is the same as multiplying by 1 over x cubed. So what happens in the numerator, with this action, this goes away, minus the radical remains. For the denominator, 2 over x cubed, and this one, minus 1. So now, if you replace the x with negative infinity, this piece goes to 0, this piece goes to 0. So the numerator being negative 2, the denominator would be negative 1, and the answer is positive 2. The answer is positive 2. So a quick recap. Absolute value of x squared is absolute value of x. It becomes x if x is positive, for example, x is approaching infinity. It becomes negative x if x is negative, for example, x is approaching negative infinity. We don't have to worry about it when x is approaching infinity. So we have to be careful when x is approaching negative infinity. I can't emphasize this enough. I'm going to look at a similar question. This time x is approaching infinity. And again, I'm reminding you that in case of a limit, as x approaches infinity, for x larger than 0, absolute value of x squared is absolute value of x over x. But if it's approaching negative infinity, it's a different story. So what we are going to do, since the top has x squared, and we notice that we have x to the power of 4 in the denominator, we're going to take out x to the power of 4 in the denominator as a factor. And the format is this. I hope everybody is following this type of factoring, which is not normal. Normally, we don't do that. But this is to help us evaluate the limit. I can't emphasize this enough. Normally, we do not use this methodology, but in any way. So since x is approaching infinity, I can take this out as simply x squared. So x squared equals square root of x to the power of 4 when x is larger than 0. By the way, even if it's approaching negative infinity, because the expression x squared is positive, it comes out as positive x squared. If you look at the previous case, it ended up being x cubed outside, and x cubed, you have to go with the negative because the exponent is odd. Since the exponent is even here, even if it were approaching negative infinity, you would take it out as minus x quantity squared, which is x squared. It still becomes x squared. That is extremely important to know. But nevertheless, we divide the top and the bottom by x squared now by dropping the common factor of x squared. drop the common factor of x squared, everybody. So when we do that, the numerator gives us just 1. And if you look at the bottom, you have 1 plus 0 because 1 over x to the power of 4 is 0. So it's important to know this one becomes 1 over the square root of 1 plus 0, and the answer is 1. That's how we arrive at the answer. And so the answer in this case ends up being 1. We want to find the derivative of the function, again, using the definition. F prime of x is the limit of f of x plus h minus f of x over h. So how do we write this part? So f prime of x is the limit as h approaches 0, and this part we write as 7 times x plus h quantity squared plus 4 minus this expression, 7x squared plus 4 over h. So the main part is that we should be able to write this. If we can't write this, everything will be wrong. And so the next step is to raise this to the power of 2x plus h squared is x squared plus 2xh plus h squared. And I'm going to remind you again that a plus b squared is a squared plus 2ab plus b squared. If we happen to have a negative here, we have a negative here. So in this case, we are going to distribute the 7 first. We get 7x squared plus 14xh plus 7h squared plus 4. Now we're going to distribute the negative sign, minus 7x squared minus 4. Seven x squared and minus 7x squared cancel each other. Positive and negative 4 cancel each other. So we are left with 2 terms, 14xh and 7h squared. Remember, the problem is the h in the denominator that creates a problem because it becomes 0. In the numerator, we can factor out the h. I want you to know we can factor out 7h, but I just want to get rid of the h, so I'm going to factor out the h from the numerator. I get h times 14x plus 7h. So we're going to take the limit as h approaches 0 in this following manner. Again, I want to remind you, this is not a proper factoring. The proper factoring should be 7h times 2x plus h. But the reason I do it this way because I want to get rid of the h. Okay. Can we do it otherwise? Of course, but I'm interested in getting rid of the h, and I write this. And now if I replace the h, I get to the answer 14x. And as again, many of you know, you can come up with the answer in a split second using the power rule. But we are using the definition here. We are using the definition. That's what we must do. Here's the next example. The distance in feet of an object from a starting point is given by s of t equals 2t squared minus 5t plus 4d, where t is time in seconds. We want to find the velocity of the object from 2 to 4, which is average velocity. In short, means the total distance over the total time. That is the average velocity. And therefore, for us in this case, is S of 4 minus S of 2 over 4 minus 2. This is elementary algebra. I'm going to, so everybody's very comfortable with that. So 2 times 4 squared minus 5 times 4 plus 4d minus, then plug in 2. You evaluate each one when S of 4, in other words, replace the 4t with 4, you get 52. S of 2, replace the t with 2, you get 38. Their difference divided by 2 is 7 feet per second, units of the numerator over the units of the time. And I'm not concerned about this. I just wanted to remind you about this average velocity elementary algebra. However, we are interested in the instantaneous velocity. Now, even if they don't mention instantaneous velocity, the fact that we have only one point in time, that means instantaneous velocity, and we're going to use that. That everybody remembers the f prime of x, the limit of f of x plus h minus f of x over h. So we are going with s, whatever the function is. Doesn't have to be always f of x, in this case s of t. And specifically, I want to use 4 seconds, although you can find v in general and plug in 4. Again, I want to remind you of that format. So in this case, a is 4, and again, if you decide to find the v of a t and then at the end replace the t with 4, it's absolutely fine. So we replace the a with number 4, and we are going to plug it into this formula now using s of t. So 2 times 4 plus h squared minus 5 times 4 plus h plus 4d. I'm going to show you s of 4 means 2 times 4 squared minus 5 times 4 plus 4d. That's the numerator. I just wanted to show you. And I'm not going to evaluate this. We already know it's 52. You can check it out. What I want to show you again is everything is algebraic, and the only step that is really calculus when you evaluate the limit. So this expression, writing it as such, or algebra. And at the end, when we evaluate, the limit becomes calculus. So 4 plus h squared, as you know, it's 16 plus 8h plus h squared. And so if we multiply it by 2, we get 32 plus 16h plus 2h squared minus 20 minus 5h plus 40, and minus, we are going to use the 52. Now notice the numbers 32, negative 20, positive 40, minus 52, they all add up to 0. So we have the numerator as 2h squared plus 11h. That's all there is to it. Numerator has 2 terms, and we're going to take the common factor of h out. And when you apply the h equal to 0, you get 11 feet per second. Units of the numerator over the units of the denominator. And the instantaneous velocity has the same unit as the average velocity. We want to find an equation of a tangent line to the parabola y equals x squared at the pair 1, 1. So in order to find the equation of a tangent line, we need a pair which is given. Sometimes they may give us only x. We can plug in the value, evaluate y. We also need the slope, and we're going to use the definition. And what I want to do, I want to use for practice, I'm going to use both definitions. One is good enough. So I'm going to show you the first definition. So M is f prime of A, and I write the first definition. So A is 1, the x coordinate of the given pair. A is 1, the x coordinate of the given pair. And now we replace f of x with x squared as far as f of 1 is concerned. If it's given, we write it. If it's not, we plug it in and we evaluate it, just for the sake of argument. Let's say x was 5, then when you plug in, you get 25, okay? Since x is 1, y is also 1. So we write x squared minus 1. As you can see, it's a squared minus b squared. It can be factored into a minus b, a plus b, so it becomes x minus 1, x plus 1. So we can drop the common factor of x minus 1, and now we replace the x and we get to 2. And that's all there is to it, because if we have a pair and a slope, y minus y1 equals m times x minus x of 1, that means y minus 1 is m2 times x minus 1. And this would be 2x minus 2. We add 1, and we get 2x minus 1. So y equals 2x minus 1, and again, the pair belongs to the original function, also belongs to this tangent line. So if you plug in 1, you get y equals 1. That's how you check it. But what I want to show you is I use this one to find f prime of A. I'm going to show you also this one for practice, and I'm going to emphasize that it's a good idea to know both methods, and sometimes one may be easier than the other. But most of the time we use this one. So with that being the case, A obviously is 1, so we replace the A with 1. So we are using this definition, and again, basically they are the same. And so we are going to plug 1 plus h into the function y equals x squared, and it becomes 1 plus h squared. F of 1, we already know it to be 1. So this is 1 plus h squared. Now we are going to square this. 1 plus 2h plus h squared. So far, so good. Very straightforward. 1 and negative 1 cancel each other, obviously. And the numerator, we can factor the h out. If we factor the h out, we get h times 2 plus h. And again, we can drop the common factor of h. And if you plug it in, you get 2. What I want you to notice is that obviously, as expected, is the same as what we did here. Which one is easier really depends on the function. Sometimes this one is easier, sometimes this one is easier. You have to be comfortable with both to be on the safe side. And happy studying, everybody.